Hello and namaste everyone. Welcome to lecture 3. Let's do a quick recap of what we have covered in lectures 1 and 2. In lecture 1, we discussed an example of stochastic approximation which involved estimating the mean of a random vector x using samples of the same random vector x. Then in lecture 2, we began looking at a more realistic setup where the goal was to estimate the expected value of some random vector x using samples of another random vector y, right. More specifically, we looked at the problem of estimating the rate at which the web page changes. Okay, so this was the problem that we considered, and formally we described this problem in the following way. We presume that Tn, the sequence Tn, that means T0, T1, T2, T3 and so on and so forth, right. This denotes the time instances at which the web page changes, and then for simplicity we had presumed that this sequence forms a Poisson point process on the positive or non-negative real line with rate lambda, right. And I had told you that the sequence Tn is said to be a Poisson point process if the interchange times, that is Tn plus 1 minus Tn, that sequence for different values of n forms a sequence of independent and identically distributed exponential random variables with parameter lambda, right. And then we said we don't have access directly to the times at which the web page changes. Instead we said that often we may only be able to access the web page at time instances Sn, right, and at time instance Sn plus 1 we only get to know if the web page has changed in the interval Sn to Sn plus 1. In particular, at time instance Sn plus 1 we said that we have access to the value of the random variable In plus 1, which is a 0-1 random variable, 0 if the web page has not changed between Sn and Sn plus 1, and 1 if it has changed at least once. So recall that NAB equals the number of values in the set described over here. So this set includes all those values of n where Tn lies between A and B. So n of AB is the cardinality of this set, and I denote cardinality by this hash variable, right. So this is what I use over here, this definition is what I use over here, right. And notice that Sn plus 1, these are all random variables, right, and n of Sn comma Sn plus 1 is another random variable, right. So now our formal question is, can we estimate lambda, which denotes the rate at which the web page changes, using values of the 0-1 random variables I1, I2, I3 and so on and so forth. So let us get a pictorial view of this problem. So imagine this black line to denote the time axis, right, and the red crosses. So you can see that there are a bunch of red crosses, right. So let's presume that these red crosses denote the times at which the web page changes, right. So you can see that so T0 is basically some initial point of convenience, so don't read too much into T0, we will presume that T0 is 0, right. So T1 is from this chosen time of reference is the first time at which the web page changes. T2 is the second time instance at which the web page changes. We can have similar interpretations for T3, T4 and T5. Notice that the distance between T0 to T1, T1 to T2, T2 to T3, they are not the same. This is on purpose because recall that if T0, T1, T2, T3 and so on form a Poisson point process, then the interchange times, that is T1 minus T0, T2 minus T1 and so on, they themselves are exponential random variables, right. And because they are random variables, the width of these intervals will be different, and each time you repeat this experiment, these positions of T0, T1, T2, T3 and so on will differ, right? And for this particular instance of this experiment, let's presume that the places where I have put crosses are the times at which the web page changes, right? On the other hand, we have the time instances denoted by these blue circles at which we access the web page. So again, for convenience, we say that S0 is 0 and that matches T0, right? So we access from this reference time this web page at time S1, S2, S3 and so on, right? And again we can presume that either S1 minus S0, S2 minus S1, they are regularly placed, right? Recall that this S0, S1, S2, this is something that is there under our control, because we are designing a web crawler that visits this web page, right? So we are designing this crawler and we can choose how often it can visit this web page, and should it visit it at periodic intervals of time or should it visit it at random instances of time. All this is under our control. On the other hand, I mean T0, T1, T2, T3 and so on, they are not under our control. That's the time instances at which the web page changes, which is beyond our control. But S0, S1, S2, S3 and so on, they are indeed under our control, right? Now as I told you, I1 is the 0, 1 random variable which tells us whether the web page has changed between S0 and S1. Now in this case you can see that there is no cross which is strictly bigger than S0 and less than equal to S1, and that is the reason I1 is 0, right? On the other hand, I2 looks at whether the web page has changed between S1 and S2, right? And you can see that there are two crosses between S1 and S2, that means the web page changed twice, right? But I1 will only be 1, because we will look at the copy of the web page at time instance S2 and compare it with the copy of the web page that we had accessed at time instance S1, and we will only see that the web page has changed. Because of this reason, this I2 will only be 1 and not be 2, right? And similarly I3 is 1 because there is exactly one time instance between S2 and S3, that is T3, at which the web page changed, right? On the other hand, between S3 and S4 there are two time instances at which the web page changed, hence I4 is again 1, right? So the question is, given values of I1, I2, I3, which again notice that arrives sequentially, can we come up with a stochastic approximation algorithm to estimate lambda, right? Now as I told you, the time instances at which we visit this web page is under our control, so we could choose it to be regularly placed. However, for ease of analysis, we will presume that Sn, that is the sequence Sn, which is the time instances at which we access the web page, is actually another Poisson point process, but we will presume that this is a Poisson point process with a known rate p, right? So we will presume that, okay, and I should add that this process, we will presume is independent to the Tn process, right? So now under this assumption our goal is to estimate lambda, right? So before we discuss the algorithm to estimate lambda, what we will do is we will first estimate or first understand the properties of the sequence In, okay? So we will do that now. Okay, so recall that In is actually a 0, 1 Bernoulli random variable. So let us try to compute its expected value, right? Now by the properties of iterated expectation, one knows that expected value of In plus 1 is the expectation of the expectation of In plus 1 under the conditioning that Sn plus 1 minus Sn equals tau, Okay, so recall that Sn plus 1 minus Sn, because of our choice that the sequence Sn is a Poisson point process with rate lambda, Sn plus 1 minus Sn will be exponential with rate p, right? The times at which the web page changes is a Poisson point process with unknown rate lambda. However, the times at which we access the web page is a Poisson point process with rate p, hence Sn plus 1 minus Sn is an exponential random variable with parameter p, right. So our goal is, given that Sn plus 1 minus Sn equals t, what is the conditional expectation of In plus 1? Now recall that In plus 1. So let me go to the previous slide to explain this. Okay, so recall that In plus 1 tells us how many times the web page changes between two successive visits, in particular between Sn and Sn plus 1. And now under this conditional expectation, what we are saying is that, suppose this time interval is of length tau. Okay, so we are presuming that the length of time over here equals tau. Given this information, what is the expected value of In plus 1, which is equivalent to asking when is In plus 1 equal to 1, because In plus 1 is a Bernoulli random variable, right. So we want to compute the expected value of In plus 1, and from the basic properties of expectation, we know that the expected value of In plus 1 can be written using the iterated expectation property, that is expectation of In plus 1 given Sn plus 1 minus Sn equals tau. Now recall that because the times at which we access the web page is a Poisson point process with known rate p, this Sn plus 1 minus Sn would actually be an exponential random variable with rate p, right. And let me now tell you how to find this expectation. So I have given you the expression over here, right. So the outer expectation basically figures out what's the probability that Sn plus 1 minus Sn takes the value tau in a small interval. So this is given over here, this times d tau, right, and this inner conditional expectation is given in this round bracket. So let me now explain how this inner conditional expectation is found out, right. So the inner conditional expectation, because your In plus 1 is a Bernoulli random variable, actually equals the conditional probability that In plus 1 equals 1 given Sn plus 1 minus Sn equals tau. Now this probability equals 1 minus the probability that In plus 1 equals 0 with the same conditioning. Okay, the same conditioning that we have over here, place it over here. Now In plus 1 is 0 if and only if there are no changes in the interval starting from Sn and the one that ends at Sn plus 1. So that is what I have written over here. So this probability and this probability are one and the same, right. And because your the times at which your web page changes and the times at which we access the web page, these two processes are independent, one can show that this probability actually equals e raised to minus lambda tau, right. So this just follows from the fact that a Poisson random variable, right, like if you take this AB interval and if you ask what's the probability that this is 0, so because you have a Poisson random variable, this is e raised to minus lambda times b minus a. Okay, so this is exactly what I have written over here, and this b minus a gets replaced by tau because of this conditioning over here. Just a minute, let me try this again. Because of this conditioning over here, right. So that's why you end up with this e raised to minus lambda tau, and this just follows from this expression. So now let me erase all these quantities over here. All right. So this integral by a simple calculation can be seen to be 1 minus p over p plus lambda, which if you rearrange and do a bit of algebra can be seen to be lambda over p plus lambda. Okay, so recall that this is the expression for expected value of in plus 1, right. Now since the right hand side over here, which I abbreviate as RHS, does not depend on n, right, one can conclude that the sequence in is actually a sequence of independent and identically distributed Bernoulli random variables with mean lambda over p plus lambda, which is the expression that we had found over here, right. So now what we are going to do is we are going to make use of this observation and come up with an algorithm to find lambda. Okay, so this is our goal now. So let's see how we can go ahead and do that. Okay, so now in order to come up with this algorithm, let me first define a function f. Okay, so this function goes from the real line to the real line and is given by this definition over here, right. It is p over 2 times lambda plus p x minus lambda the whole square, right. And so how we came up with this function and so on, I will talk about it, but at this point bear with me and let's say f is some r to r function given by this expression. So if you look at grad f of x, then you can see that this expression is basically p over lambda plus p times x minus lambda. Okay. Now the expression for gradient of f of x is unknown, right, at any x, since lambda is unknown. So we don't know lambda, hence the value of grad f of x is unknown. However, if we define the noise sequence mn plus 1 using the expression on the right, okay, I will tell you how this noise expression came about and so on and so forth, but bear with me for the time being. If we define the noise expression using the following formula, that is in plus 1 times xn plus p minus lambda over lambda plus p times xn plus b. Okay, so at this point you can just note that this in plus 1 that you have over here, its expected value is written over here, and these two expressions are basically one and the same, right. So you can sort of see the nice structure that mn plus 1 has, right. And now if you look at the expression for minus grad f of xn plus mn plus 1, then you can see that mn plus 1 from this above expression equals what is given over here, right. Okay, and the value of minus grad f of xn from this equals this expression over here, right. And you can see that these two terms actually cancel off, and hence by a simple algebra one can see that whatever remains, that is this expression and this expression, if you combine them you can see that we end up with this expression, right. So at this point I am sure as a reader you wouldn't know why did we choose this f function, why did we define mn plus 1 to be in this form. However, what you can observe is this expression for minus grad f of xn plus mn plus 1 is what is given over here, and this expression can be computed at the time step n. It can be computed because at time step n, which in the real line corresponds to the true time instance Sn plus 1, we would know the value of In plus 1, and since we would have already computed xn, we would also know xn, and p is the rate at which we access the web page. So this is also something that we know. So one can see that every term in this blue box is actually known, hence this expression is known, right. So while grad of f of xn is unknown because lambda is unknown, the value of minus grad f of xn plus mn plus 1 is known, right. In other words, while the required gradient is unknown, a noisy estimate of this gradient can be obtained by just looking at the values of in plus 1, xn and p, right. So this is in some sense the advantage of working with this f and this noise variable, right. You can actually get hold of more details about this algorithm, which I had had the opportunity to work on as part of this paper with my collaborators Professor Konstantin Evrechenkov and Kishore Patil. This is the name of the paper in which we had designed this algorithm, and if you are interested, you can go to my Google Scholar profile and get hold of this paper and read the details further. Okay. So at this point what we have is that while minus grad f of xn is unknown, right, because lambda is unknown, but minus grad f of xn plus mn plus 1 equals this quantity which is known at time step n, and this can be viewed as a noisy estimate of minus grad f of xn, right. So in order to estimate lambda, we can consider now the following algorithm. Okay. So let me go over this algorithm. This algorithm is xn plus 1 equals xn plus alpha n times the square bracket minus grad f of xn plus mn plus 1. Indeed, we do not know grad f of xn, but as we have pointed over here, right, the sum of minus grad f of xn and mn plus 1 is indeed known at the time step n, which corresponds to the true time instance sn plus 1, right. So while this is not known, this sum is actually known, right. So we can actually run this algorithm using just the values of in plus 1, right. And in that paper that I showed you in the previous slide, we have actually shown that xn converges to lambda, which is the quantity of interest, almost surely. Is this okay? So the almost surely part comes in here because xn is a sequence of random variables, and when we talk of convergence of random variables, we have to use some appropriate quantification, and you will soon see that when we discuss the convergence of stochastic approximation algorithms, okay, what do we mean by this almost sure convergence and how we can prove this. Okay. So at this point you only have to note that this xn update rule is actually nice. It is nice because even though you don't know grad f of xn, it is making use of a noisy estimate of grad of xn, which only involves quantities that you know, right. So that's what is good about this algorithm on one hand. In other words, you can actually implement this algorithm. On the other hand, using the theory of stochastic approximation, we will see later that one can show that this xn actually converges to lambda. So lambda is the quantity of interest to us, and this algorithm actually converges there, and hence this will be a useful algorithm. Okay. Now one thing that I have not dealt too much time on is in trying to understand what is good about this noise sequence or noise term mn plus 1. Okay, I just gave you a hint that if you take the expectation of in plus 1, then you get this lambda over lambda plus p. Okay, so this is something that I mentioned, and then this xn plus p term is same in both the first summand and the second summand. Okay, so other than that I have not told you, but you will soon see that this mn plus 1 is a nice noise sequence, nice in the sense that you can apply lot of existing mathematical theory to understand the behavior of this noise term mn plus 1, right. So this is something that we will understand in the future classes, right. So now let me finish this lecture 3 by summarizing what we have done so far, right. So far we have seen two examples of SGD methods. Okay, so I think I did not emphasize it. Even for example 2, the algorithm that we came up with is actually an SGD method, that is stochastic gradient descent. And as I have mentioned in the first class, SGD methods are special cases of stochastic approximation methods, right. Now we have looked at two examples. In example 1, we looked at the case of estimating expected value of x using samples of the random variable random vector x itself. In example 2, we looked at estimating the expectation of a random variable x, right. We wanted to estimate this quantity lambda, which in some sense the inverse of this was the expected value of the interchange times, that is Tn plus 1 minus Tn, and we use this we did this estimation using samples of another random variable y, right. In this case the random variable y that we had access to were these in plus 1s, right, I1, I2, I3 and so on. So we made use of these values to estimate something about lambda, right. And we also noted that in the two examples the true gradient was inaccessible. It was unknown because it depended on quantities that were unknown, right. But one could access a noisy estimate of these negative gradients, right. And because we could make use of these noisy estimates, we can actually run these SGD methods in practice. Okay, even though we don't know these unknown quantities, in particular we don't know these unknown gradients, we can actually run this algorithm, and in the future lectures we will see how we can analyze these algorithms. In particular we will see how we can understand the convergence of these algorithms, right. So that is one thing we will discuss in the future class. In the next class we will also try to see an example of a stochastic approximation method which is not an SGD, right. So as I told you, SGD methods are a special subclass of stochastic approximation methods. However, the true power or potential of stochastic approximation lies in the fact that we can also view them beyond the standard SGD methods. Okay, with this let me stop. Thank you and namaste.